Swayam Prabha. Digital India. Educated India.
Okay, so we talk about some recent stream cipher, some modern stream cipher. So we have seen the stream cipher, general structure of a stream cipher. This is basically, there are two types of streams. One is synchronous stream cipher, synchronous stream cipher. So in synchronous stream cipher, what we have a finite state. It could be some state ST, which is initialized by the secret key shared between Alice and Bob. Shared between receiver and sender, and then it is, and then we have a state update function, which is taking the, and it is, there is a function S which is taking the that content of the state, and it is giving us the key stream. So this is the key stream, TF key stream, and then it is XOR with the plain text bit PT, and we get the CT, hypertext bit. I see a TF hypertext within the TF clock. So in the modern stream cipher, apart from this secret key shared between Alice and Bob, what we have the IV, initialization vector, which is also another secret which is shared between Alice and Bob. So this IV is used as a, this is called initialization vector. This is used in the this initialization method of the stream cipher. So what we do, we take some initialization vector and we will put it as a part of the key with the key secret key. We will use this to initialize the state, and then we run the key stream for some clocking, up to some clocking, and then finally we get the initial state of the LFSR. Is this clear? Earlier, the initial state of the LFSR is direct the secret key shared between Alice and Bob. So now this, if we do that, then it is a candidate of what is called time memory trade-off attack. So to prevent that, we want to increase the size of the secret. To increase the size of the secret, the IV is introduced. So we use this IV along with the secret key, and we put it into the state, and we run these states, we clock this state for some number of times, and then we take that, after running this state in some number of times, then we take that value of that state as a initial state. Okay, so that is that every modern stream cipher has this IV, and we put this IV along with the key into the state, and then we run this G, the state updation function, some number of times, and then we reach to the initial state. Then after reaching this is called initial state. Then after reaching the initial state, then we start generating the key stream. This is called initial state. Initial state is getting after running this few number of times, after putting this IV and the key into the finite state machine. Then we clock it many times, and then we stop. Now this is our initial state. Now after this, we keep on running to get the key stream. So that is the idea. So let us talk about some stream cipher, some modern stream cipher which is using the IV and this key stream. So this is the stream cipher Snow. So this is a LFSR. This is basically a 16-bit LFSR which is connected by this bit, and this is S1 to S16, and we have a alpha. We will discuss what is alpha. And then as a part of it, we have the register 32-bit 2 register R1 and R2, and this is a S box, and this is a simply bitwise XOR operation, and this is the addition operation mod 2 to the power 32, and this is the circular shift. So these are operations in the SNO 1, and then finally we take this bit along with this and we XOR these two and get the key stream bit. So this LFSR is 16-bit LFSR, and this finite this is, and we have a this is a finite state machine. This has two registers, R1 and R2, and the operation will be calculated output to the next state, the value of, by taking the value of R1 and R2. The first key initialization is done. This procedure provides the initial value of the LFSR as well as for the R1 and R2. So we are initializing everything, LFSR and the register R1 and R2, which are 32 bits. Next, first 32 bit of the key stream is calculated by bitwise adding the output of this finite state machine and the last entry of the LFSR. That means this one. So this is last entry, and this is the output of this, what is final. We are telling this as a machine, finite state machine. This output will be XOR, and we are outputting this 32-bit key stream. After that, whole cipher is clocked once, and next 32-bit of the key stream is calculated by again bitwise adding the output of the finite state machine and the last entry of the LFSR. We clock again to continue this fashion. So each time we are getting 32 bit like this. Okay. And the LFSR here we are taking is a primitive based on a primitive polynomial over f2 to the power 32, and this polynomial is of this form. So this is a 16-bit LFSR. So f16 plus f13 plus x to the power 7. So this x to the power 7, there is a mistake, plus alpha to the power minus 1. This alpha is basically root of this irreducible polynomial. So this is a irreducible polynomial over f2 to the power 32, and alpha is a root of this polynomial. So this alpha, we are taking alpha inverse of it. Okay, so this is the LFSR we are choosing in SNO 1, and these are the state of the LFSR. This is basically, LFSR is basically a flip-flop. So these are the flip-flops, and we have the output of the finite state machine called FSM out. It calculated by this, because it is just S1 is the S box. It is operating with R1. This is the addition operation, and then it is bitwise XORing with the R2, and we are getting output of this. And this output we are basically XORing with the, this is again 32 bit. This output we are basically XORing with this with the S16, and the key stream is finally XOR with the plain text to produce the ciphertext, that we know. Okay, so inside this finite state machine, we take a value R1 and R2, but how this state is changing in a finite state machine. So let us come back to this figure. So how the states are changing here. So this is the state updater function in the finite state machine. So it takes this R2, and then this is the shifting, circular shifting will come to that. Then it is taking R1, then XORing with that, then it is changing this R1. So then again it is changing the R2. So this is what we are doing here. So let us so this is the state update function for this state R1 and R2. So this R1 is basically f of this output we are adding with, this is the addition modulo 2 to the power 32. This is we are adding with R2, then this is the cyclic shift 7 times, and then final result we are XORing with the R1. So this is basically updation of R1, and the R2 is basically simply we have a S box. If we come to the figure again, this is basically S box which is taking the R1 as input, and it is R2 is updated by this. Okay, so this is the state updation function for this finite state machine. So this was attacked by some algebraic attack, and many cryptanalysis on the SNO 1 is there in the literature. So they proposed a new version of the SNO, that is called SNO 2. So in there they have changed the polynomial and the connection. So instead of taking alpha inverse, they have introduced alpha multiplied with alpha inverse. So this is the SNO 2. So remaining are almost same. So except this is coming from this polynomial they have changed. The feedback polynomial of SNO 2 is given by this. So they are multiplying alpha with this. Then this positions also they are changing, and then alpha inverse x to the power 5 plus 1. So this is the polynomial they have used for this SNO 2, where alpha is the root of the, so they are taking a new polynomial, root of this polynomial. So for if you take this polynomial, this is the polynomial over f2 to the power 8, and they have also beta is the root of this x. This is I think this is a polynomial they have used in English. So they have changed this. Remaining things are almost same. Only thing is the position we are changing. So this is the input is the finite state machine if this. So this is how we update the finite state machine, that R1 and R2. So this is t plus 15 and is t plus 5. Then it is basically we are st plus 15 we are adding with R1t, that is the tth, for tth clocking we are doing this. This is the addition modulo 2 to the power 32, and then this we are XORing with R2t, the tth at the tth time. This is the position of the, this is the state, this is the value in the R2 register. Okay, and then the key stream bit is basically ft XOR with the st. So this is, if you come to the figure, so this is the output. This is basically coming from the LFSR bit xt. This is XOR with this output. So this is our key stream bit. So this is our ft. Ft is the output of the finite state machine, and then xt which is coming from the LFSR, and these two are XOR to get the ZT. The register R1 and R2 update like this by the similar way earlier. So this is the S box we are applying. If you come back here, so we are applying the S box to update this. So R1 will be the same as this xt. Okay, this is ft. Ft is basically added with the R2, and that will give us the new R1. So that is the state update. And this R2 is basically we take the R1 and we apply this S box, and that will be the new R2. So this is the way how we update this. So this is the new version of the SNO. This is called SNO 2. Now we talk about another stream cipher, which is called GAIN stream cipher. So the GAIN has two versions. So this GAIN is having two parts. One is LFSR, another one is NLFSR. So this is, each of these, NLFSR means nonlinear feedback shift register, and this nonlinear, this is LFSR, feedback shift register. This is nonlinear feedback shift register. The connection is, this output is nonlinear output. So this, each of this is 80 bits. So this is a 80-bit LFSR, and this is also a 80-bit LFSR, and this nonlinear, this NLFSR is updated by the function g, and the LFSR is updating by the function f. And to get the key stream, we have a h function which is taking 4 bits from this LFSR, which 4 will come to know. 4 bits, so it has 80 bits. Among these 80 bits, we are only taking 4 bits from this LFSR, and we are taking 1 bit from this NLFSR, and we are applying this function h, and in the output we are XORing with the this bit with the NLFSR, and that is the key stream. So this is the general structure of the GAIN stream cipher, and this is basically what we are doing here. So let us talk about this. This is how the feedback function of LFSR is happening. So it is basically taking this many bits. So this is a 80 bit. So among this 80 bit, we are taking the 64 bit, 51 bit, 32, 38 bit. So these are the bits contributing in the this F function. So this is the function how we making the feedback. So this is the state updation function of the LFSR, and this is the corresponding this is the state update function for the NLFSR. This is this one, G function. So NLFSR, what we are doing, we are getting some we are getting the state from LFSR, and this is also XORing with this G of X. So G of X is taking this input of the LFSR state and apply G function, and then it is XORing with the this XT, which is the state coming from the LFSR, and then we are XORing, and that is the new bit for the NLFSR. So this is what we are doing here. So this is coming from the LFSR, and this is the way, this is our G function. So G is involved many bits from the NLFSR. So that is 62 8 bit, 68 bit, 52 bit, 45 bit, like this. So this is just all the bits are involved, and this is not a linear function. If you observe here, there are some nonlinear component over here. So this is the multiplication. I mean, so these are the this is also 4 functions, four variables are involved. So that's why this is called nonlinear feedback function. So that is our G function, this G function. So G is taking the few state of the NLFSR, and it is a nonlinear function, and then it is XORing with this LFSR function, and it is going to the NLFSR bit. Okay. So this is the update function of this is the bit which is updating the NLFSR. Okay, and then we have the H function. So H function is taking, so this is the function which is giving us the key stream H of X. So what is X? X is basically, let us go back to the picture. So H is taking how many bits? H is taking 4 bits from the LFSR and 1 bit from the NLFSR, and that is giving us, that is the input of the H, and H of X is the output here. So 4 bit from the LFSR and 1 bit from the NLFSR. So which 4? So this is our H function. So X0, X1, X2, X3, these are coming from NLFSR. So these are basically combination of this, and the remaining bits are basically, and X4 is coming from NLFSR, and this is the H function. So it is keep on updating this. So basically the LFSR, which bit? The third bit, third position, 25th position, and 46th position, and 64th position. So these are the position coming from the LFSR bit contributing in the H function, and for NLFSR it is basically 63 position. So 63. So this is 8 bit. Among these 8 bits, so 63th bit is basically our one of the input in H. So that is basically our X4, and this is the function of this. This is also a nonlinear function. We have some nonlinear terms over here. So this is making us ZT. So ZT is basically, so algebraic normal form of the key stream bit of the ciphertext after clocking is this. So now we have to talk about the initialization phase of the LFSR, I mean this gain. So how because we know in every stream cipher we just we have this finite state machine, and then we have this Alice and Bob sharing the secret key along with the IV. Now we put this IV and the secret key in the states, and then we clock the state until we reach to a initial state. Then once we reach to initial, this is called initialization step. Once we reach to the initial state, then we again then we start generating the key stream by again clocking. So depending on the size of the plain text, we need to get this many key streams. So this is the general structure. So here also we have this key initialization space. So we have this IV. So here IV key is 80 bit, which is the secret key shared between Alice and Bob are 80 bits. So this is totally we store into the NLFSR. So the key we are storing into the NLFSR, because NLFSR is also 80 bit, and the IV is basically 64 bit, and remaining, so this is LFSR is also 80 bit, and remaining 60 bit we are just putting constant like 1111. So 16 plus 64 bit IV, so this is 80 bit. So we are putting this secret key 80 bit, filling the LFSR, and 64 bit is the IV size. So we are putting this first 64 bit of the LFSR, and remaining 16 bit we are putting 1111 like this. Okay, and then we run this, for 160 rounds. We clock this system for 160 rounds, and after that we reach to the initial state. We run this for 160 rounds, then we reach to the initial state. Then after that we do the clocking to get the key stream. So that is the idea. So we just initialize this key to this NLFSR, and we take 64 bit IV to this first 64 bit, and remaining 60 bit we put 1, and this we clock this system for 160 times, and then we reach to the initial states of the LFSR and NLFSR. Then we start clocking this to generate the key string. So this is the key generation step. And now this is the another version of the game, which is called game 128A. So this A is the authentication purpose. So we use some bit for the authentication purpose. And here what we are doing, so this is a similar structure. So only thing, here we are taking the 7th bit. So this is basically 6th bit of this, and we are having the F function. This F function is given over here. So this is the feedback function. So this is the state updation function. This is the state updation function of the NLFSR. We have G function. We are taking this output, we are XORing with this, and this is basically we are updating the NLFSR. And this H we are taking 7th bit of the LLFSR, and this 2 bit from the 7th bit from the NLFSR, and 2 bit from the 7 bit from the LFSR, and 2 bit from the NLFSR, and then we apply this H, and then this is the 7th bit, and we are drawing this. So this is the function like this. So we have this x2, these are the bits, and this is our H function, and this is the state updated function for this LFSR, and this is the state update function for NLFSR. Okay, and the output will be like this. This is the output, but the key initialization step is here. Here what we are doing in key initialization step. So here also we have 80 bit, and we have 80 bit NLFSR, 80 bit LFSR. So here also secret key is 80 bit. So we put this 80 bit into NLFSR, and this is 128 bit. This is a 128 bit. So this NLFSR is 128 bit. This is also 128 bit. So our key is 128 bit, and which we put it into the NLFSR, and the IV is 96 bit. So we put this first 96 bit of the LFSR in this IV in this first 96 bit of the LFSR, and followed by all the ones, and last one is 0. So that is the initial storing of this NLFSR bit and the LFSR bit. and then we run this for 256 times. We do this clocking for 256 times, and then we start generating the key stream bit, but we just do the first 64-bit key stream we use for the authentication purpose. So after this 256 bits, after this 256 clocking, we reach to the initial state. The value of the LFSR and NLFSR called initial state. Then we can start generating the key stream. Now we start generating the key stream by clocking again, but now this is the authentication. This is also authentication is required. So we run this for 64-bit, and this 64-bit we use for the authentication purpose. First 64-bit key stream, and then remaining after that we will just start generating the key stream bit. So this is the idea. So anyway, we discussed this. Now we talk about a stream cipher, which is asynchronous stream cipher. We have seen the synchronous stream cipher, where this key stream are basically coming from the this key stream are function of the state basically. But here key stream are not function of the plain text or ciphertext. But here in the modern stream cipher, they are involving key stream to be a function of the feedback of the plain text ciphertext to avoid this algebraic attack or some other correlation attack of this. So this is a asynchronous stream cipher, where we involve this key stream, this function, even in the state update function also we involve the plain text. Okay. So one example of this is helix. So the helix, this is the stream cipher. So this is the state, and this is the next update state. So here if you see, we have used the plain text. So this is basically this is 32-bit. So this is basically bitwise XORing. This is the rotation operation, cyclic rotation operation, and these are the basically keys. So this involves the plain text. So that's why it is called asynchronous stream cipher. So this is the one state, and we get the next state. So this is one example where the state update function and the key stream generation is having involved the plain text bit. So that will avoid the some known attack, but that is little design is little complicated. So this is called asynchronous stream cipher. Thank you.